Shubham Bais, who will give a talk on vertical operators on the Bergman space over the upper half plane integral representation. Please go ahead, Shubham.
Yeah. So, am I audible?
Yeah.
Yeah. So, first of all, I would like to thank the organizers for giving me opportunity to present my work here. So, today I will be talking about the vertical operators on the Bergman space and their integral representation. So, this is a joint work with my PhD supervisor, D. Venku Naidu, and one of my colleague, Mohan. So this is the outline of my talk. So first we shall recall some of the preliminary definitions and results which will be useful throughout the talk. Then we discuss a general problem then for that general problem we go for a particular case which are nothing but the vertical operators and study the integral form of these operators followed by the references. So throughout the talk, R plus, and C denote the set of all real numbers, positive real numbers, and the complex numbers, respectively. We consider H to be a Hilbert space over a complex field C, and the norm and inner product on H are denoted respectively by these symbols. And whenever X and Y are Banach spaces, we say a linear map T from X to Y to be, we say a map T from X to Y to be linear if it preserves vector addition and scalar multiplication, and it is said to be a bounded operator if we can have a non-negative positive number m such that T satisfies this inequality, and the infimum over all such m is denoted by the symbol norm of T suffix x goes to y, and it is known as the operator norm of T. The collection of all bounded linear operators from x to y is denoted by b of xy, and if we consider x to be equal to y, it is denoted by p of x. We say a bounded operator t from x to y to be compact if we takes bounded subsets of x to pre-compact subsets of y, where we say a subset to be pre-compact if its closure is compact, and the collection of all compact operators from x to y is denoted by k of xy. Now, if x is a non-empty set and mu is a sigma finite measure on x, and if we consider H to be a closed subspace of L2 of x comma u, so since L2 of x comma u is a Hilbert space, H is again a Hilbert space, but we want something more for this Hilbert space. It should be a reproducing kernel Hilbert subspace of L2 of x comma u, which means for each z, the evaluation functional which takes f to f of z is bounded linear functional on H. And if G is a locally compact group, and we denote B of H, U of H, and Q of X to be the collection of all bounded operators, unitary operators, and compact operators on H. And the function pi from G to H is said to be a unitary representation of G on H if it is a group homomorphism, and for each side coming from H, we have that the map G going to pi of G evaluating at psi is a norm continuous function. So due to the reproducing kernel Hilbert space nature of H, what we could see is whenever we have a bounded operator T, the bounded operator can be represented as an integral operator of the form integration over x f of w kt of zw d mu of w, where the integral kernel kt is exactly inner product of kz with tkw, and in fact it also satisfies these two conditions. So since the kernel satisfies these two conditions, the representation of t in this integral form becomes unique. So we are interested to study this kind of unique integral representation for a class of operators in biology. So what we could see is, since every operator on H is an integral operator, we can ask a general question that can we characterize all the functions on K cross on X cross X such that the integral operator given by 1 is bounded. But asking this kind of question for a general bounded operator is too much. So what we could see is, can we say something about a nice subclass of this P of H? So the first sub things what we could see is, if we start with J to be a commutative C star subalgebra of D of H, then in that case, can we say something about this K for the operators coming from J? Or else, suppose G is a globally compact group, what we have seen before, and suppose pi is the unitary representation of G on B on H. Then, if we consider the collection of all bounded operators on H such that they commute with the pi suffix G, then can we say something about the kernels for the operators in this class? So in this talk, we are basically concentrating on the second sub questions in a particular class of Hilbert space. So in our framework, we consider the non-empty set X to be an upper half plane, which consists of all complex number complex number Z, such that their imaginary part is bigger than zero, greater than zero, and mu is the Lebesgue measure on pi, and L2 of pi d mu is the Hilbert space of all Lebesgue measurable functions on pi, such that they are square integrable. We denote the holomorphic function on pi by O of pi. Then the Bergman space A2 of pi is nothing but all those functions in L2 pi which are holomorphic. So what is known is, this A2 pi is a reproducing kernel Hilbert space, and the kernel of this space is precisely -1 by pi z minus w bar whole square. So in our setup, our Hilbert space H is nothing but A2 pi, and we consider the group G to be R, which is locally compact abelian group, and our representations pi suffix G are precisely H suffix H, which are given by H suffix H of f at Z is nothing but f of Z minus H. So since the Lebesgue measure is real translation invariant, we can easily see with the help of change of variable that these operators are unitary operators, and they are also known as horizontal translation operators. So if we consider the representation, unitary representation of R on A2 pi given by H going to H of H, then we can ask a similar question that, can we characterize all the bounded operator T such that T commutes with all the horizontal translation operator? So here one thing to mention is, a bounded operator T on A2 pi is said to be vertical if it commutes with all the horizontal translation operator. So this class of operators are basically studied in the paper 2013. Now, suppose if we want to characterize the operators in this class, so we should have some guess that to start with what kind of kernels to consider. So what we observed is, whenever H belongs to R, the operators H suffix X also belongs to the collection V. So since they belongs to V, and we know that it is A2 pi is a reproducing kernel Hilbert space, using the reproducing nature, we could see that HH of F can be represented as an integral operator, with the integral kernel is precisely -1 by pi z minus h minus w bar. So here it should be w bar square, and there is a typo. And if I define a function phi suffix h of z to be -1 by pi z minus h whole square, then the operator hh can also be written as an integral operator of this form, where the integral kernel is precisely pi suffix h of z minus w bar. So what we could observe is this phi suffix h is an analytic function, but it doesn't belongs to A2 pi. But if we consider phi h as a function of z while fixing w, it belongs to A2 pi. And if we take the conjugate of phi suffix h and fix z, then as a function of w, again it belongs to A2 pi. So motivated by this property of the function ph, we define another class of operator, which are precisely v phi f of z is equals to this integral operator with the kernel phi of z minus w bar. But the phi we consider from a class omega, and omega is nothing but all those analytic functions on pi, such that the phi has these two properties. So what is the use of these two properties? Whenever we have phi coming from omega, the k phi having these two properties implies that v phi is well defined, and the domain of v phi is at least dense in A2 pi. So another question here, what we could ask is, can we characterize such symbols phi in omega such that the operator v phi is bounded? So our main aim is to characterize the kernels for vertical operators. Now here we have defined another class of integral operators, and we are asking the similar kind of question for this v phi. So later we will see that these are actually related. In fact, all the vertical operators are precisely of the form v phi. Before that, let us recall some definitions. So whenever f is coming from L1 intersection L2 of R, then its Fourier transform is nothing but an integral operator with integral kernel e power minus I x phi. And it is known that this operator can be extended as a unitary operator on L2 of R. Also, Bergman type transform R is introduced in the paper in 1999, which is a onto-isometric isomorphism from L2 of R plus to A2 of pi. So what we could see is this V phi satisfies certain properties. For example, whenever your phi 1 and phi 2 are coming from omega, such that V phi 1 and V phi 2 are bounded, then the two operators are same if and only if the corresponding symbols are same. So in that way, we have a unique such symbol. Also, whenever phi coming from omega and V phi is bounded, it is also a vertical operator, which means the collection of all bounded V phi is a subset of all vertical operators. And it is known from the paper in this 2013 paper, where it is shown that whenever T is a vertical operator, there exists sigma coming from L infinity of R plus, such that T can be written as R m sigma R star. So what we could see is whenever we expand this R m sigma R star, it takes the form of V psi, where psi and sigma having this relation. But in this case, we are not sure, means here we are not, it is not known that whether the psi is an element of omega or not. Since we don't have this thing with us, whether the psi coming from omega, we cannot say about the this representation is unique or not. But we actually prove in the next theorem that the psi belongs to omega. So the lemma 2 says that the collection of all V phi is nothing but subset of vertical operator, and lemma 4 says that every vertical operator is of the form V phi for some phi coming from omega. So combining these two inclusions, we'll get that all the vertical operators are of the form V phi. And lemma 1 gives that the representation of phi is unique. So it is enough to show that so it is enough to show that the symbol psi having the properties such that it should belongs to omega.
So basically you characterize this all psi that generate vertical operators.
Sir, can you repeat once?
You characterize here all functions psi that define vertical operators.
Yes. So from here, actually, when we consider m sigma coming from L infinity of r plus, we get r m sigma r star has some form. So from here also, like what should be psi is known, but this psi coming belongs to omega is not known. So in this theorem, we are showing that this psi actually coming from omega.
Another question. If you consider function psi from L infinity, they have the structure, this L infinity of the sister algebra. Can you give some algebraic operation on your function psi?
Algebraic operation on psi.
Because sigma, you know, all your sigma belongs to the sister algebra L infinity on R. And each sigma generates psi. Can you somehow translate this operation on sigma to operation on psi?
We tried something like whether the point-wise, whether it is like a multiplicative or something, but we won't get it. Yeah, like for example, suppose if I start with sigma 1 and sigma 2 as two L infinity of r plus element, then we have associated that m sigma 1 and m sigma 2. So since m sigma 1 and m sigma 2 are commutative, we can think of m sigma 1 composition m sigma 2 as m sigma 1 sigma 2. So the associated that will get some psi, which is integration over r psi sigma 1 of psi sigma 2 of psi e power I z psi d psi. But this we cannot write as a product of something in terms of psi 1 and
no,
psi 2.
it's not standard operation. Should be something different.
Yes. So in that way, we tried finding whether it has some other properties, but we did not get any concrete results in that direction.
Okay.
Yeah. So now here our aim is to show that this psi belongs to omega. So first of all, we fix some w equals to u plus iv from upper half plane. And whenever z is of the form x plus iy, we define a function phi of z minus w bar, and we use the short form as p suffix w of z as the integration over r plus psi sigma of psi e power I z minus w bar psi d psi. So the first kernel property says that this phi suffix w should belongs to A to pi, means the Bergman space. So first we have to show that this function is a continuous function. Then we'll show that it is analytic function, and then in the third step we'll show that the Bergman space norm of this phi suffix w is finite. So here we have that this function is well defined, because when we consider modulus of pw of z, and if we consider z as x plus iy and w as u plus iv, then adjusting and using the inequalities, we will get that this modulus of pw of z is dominated by this L1 function, which is integrated. And is the screen visible completely?
What?
The screen is visible completely?
Yes. It's okay.
Okay. So now if I consider z as x plus iy. And since we are in a metric space, we can use the sequential approach to prove the continuity of a function. So we consider a sequence Zn of the form xn plus iyn that converges to z. So whenever Zn is converges to z, we will get that the function fn of psi will converge to f of psi pointwise almost everywhere on R plus. And when we consider modulus of fn minus f of psi, we will get that it is dominated by an L1 function psi of e power minus v. So this function g is an L1 function. So we can use dominated convergence theorem to show that the integral over R plus of fn minus f goes to 0 as n tends to infinity. But the integration over R plus fn of d psi is nothing but phi w acting at Zn. And integration over R plus f of psi d psi is exactly phi suffix w acting at Z. So from here we get that phi w is phi w of Zn converges to phi w of Z. Since Zn is arbitrarily chosen a sequence, we will get that phi w is continuous at Z. And again, since Z is arbitrary, we will get that the function phi w is continuous on pi. Now we want to show that the function phi w is analytic on pi. So for which we are going to use the Morera's theorem. So if I start with any simple closed contour gamma, then what I need to show is integration over gamma phi w of z dz should be equals to 0. So using the form of phi w of z, we'll get that we have these two integrals. And here we need to interchange these two integrals. So that with respect to gamma, since as a function of z, the integrand is analytic, so we'll get 0, and altogether the integral value is 0. So to interchange these two integrals, we use the Fubini's theorem. And the Fubini's theorem is applicable because the integration over gamma, integration over R plus modulus of the integral d psi, and then this mod of d of z is a finite quantity. So again, here when we write z as x plus iy and w as u plus iv, we get that it is equals to psi integration psi e power minus y plus v psi d psi of this. And since gamma is compact, this integral is finite. And since psi e power minus v psi is L1 function, the first integral is also finite. So altogether, we'll get that the integral is finite. Okay, so here so far we showed that this feed suffix w is an analytic function. Now we need to show that it belongs to A2 pi. So we consider the L2 norm of this phi suffix w, and when we expand this z minus w bar, we'll get that this integral is same as this integral with the inside integral is over R plus. So what we want to do is we want to change this inside integral to integral over R. So we define a function sigma 1 as sigma when x is greater than or equal to 0 and 0 otherwise. So with the help of this, the above integral we can rewrite as rewrite in such a way that inside integral is over R, and the integrand we denote it as phi f of f suffix y comma v at psi as this function. And this inside integral, if we use the inverse Fourier transform, then it is precisely the inverse Fourier transform of f suffix y comma v acting at x minus u. And if I write pi as integration over r plus and integration over r, and if I take the integration over r here, then what we can use is the L2R is translation invariant. So, and the Plancherel theorem for Fourier transform over R we can use. So the inside integral is same as the L2 norm of f suffix y comma b acting at psi. So which is nothing but this integral, because the e power I, sorry, now again this from sigma 1 to, so we use sigma 1 so that we can go to R, and from R plus to R, and now again we can come back after using the Plancherel theorem to R plus. Now when we consider this integral over R plus, we have the inside one is finite, and the outside integral with respect to R plus is again finite. So what is helping to show that this v suffix w is a2 pi is the w precisely, because at the end we are going to get that integration over R plus psi of e power minus 2 d psi is finite. So the v is coming from w. So one more thing to observe is if we consider phi suffix w of z, which is same as phi of z minus w bar as this quantity, and if we take the conjugate of that, so it is same as something psi of psi suffix z of w, where the means I can write it as psi suffix z at w, where the sigma I can replace by sigma bar, but sigma bar is again an L infinity function. So the proceeding in the same way, we can show that even the conjugate of this, if I take, it is the a2 pi element as a function of w. So in some way, it is giving a symmetry with respect to z and w. So now it is remain to prove that the symbol phi is a different is an analytic function on pi. So here we show that if I consider any z naught from pi, then the function phi is differentiable at z. So when z naught is fixed, we consider epsilon greater than 0 such that the wall with center z naught and radius epsilon is again a belonging to pi. And w naught is chosen in such a way that if we translate this wall with w naught bar, still it belongs to pi. It is a subset of pi. So now whenever z is coming from this u of z naught comma epsilon, or even a smaller subset u of z naught comma epsilon by 4, for those z, we see that limit z tends to z naught, p of z minus p of z naught divided by z minus z naught. This limit is same as the derivative of phi suffix w naught at the point z naught plus w naught. Now the way we have chosen z naught, z, w naught bar, we get that phi w naught is an analytic function at z plus w naught bar. So this quantity is finite, this limit is finite. And hence we get that our original limit z tends to z naught, phi of z minus phi of z naught divided by z minus z naught is finite. So this implies that the function phi suffix w naught is an analytic at the point z naught plus w naught bar, and it ultimately implies that p is differentiable at z naught. So again, the differentiability of, while proving the differentiability of phi, we are using phi of w naught for some w naught. And since z naught is an arbitrary element of pi, we get that p is analytic on pi.
Okay.
So we have this boundedness result. So whenever phi is coming from omega, the integral operator v phi we defined in equation 2 is bounded on a to pi if and only if there exists sigma coming from L infinity of r plus such that phi and sigma satisfies these two. Phi and sigma satisfies this relation. In fact, we'll get that operator norm of v phi is same as the L infinity r plus norm of sigma. So this follows from lemma 2 and 4 as I explained before. Like first we show that v phi is a subset of or vertical operator, and then we can show that every vertical operator is of the form v phi. Then due to the fact that the symbol phi is coming from omega, the representation is unique. So we'll see some applications of this result. So for that first we recall some preliminary definitions. So if H is a Hilbert space and B of H is all bounded operators on H, then T coming from B of H, we say that the spectrum of T consists of all those scalars lambda from C such that T minus lambda inverse is not bounded operator. The point spectrum of T consisting of all eigenvalues of T, and we say a number lambda coming from spectrum of T to be an approximate eigenvalue of T if we can have a sequence of unit vectors coming from H such that T minus lambda xn goes to 0 as n tends to infinity. And the collection of all approximate eigenvalues of T gives the approximate point spectrum of T. And it is easy to see that the point spectrum of T is a subset of approximate spectrum of T. If we consider range of T and kernel of T, if we denote it by these symbols, then we say a bounded operator T on H to be freedom if range of T is closed and kernel of T and kernel of its adjoint of T are finite dimensional. And the essential spectrum of T then is defined to be a collection of all those scalars in C such that T minus lambda I is not freedom. And whenever we have T to be a bounded operator on H and M is a closed subspace of H, then we say that it is an invariant subspace of T if T maps M into itself, and it is said to be reducing subspace if if M is invariant under T as well as its adjoint. Equivalently, we have that since M is a closed subspace of H, associated to that we have a unique orthogonal projection. We denote it by PM. Then for a operator T coming from B of H, the set M is invariant subspace if and only if this equality holds, and it is said to be reducing subspace of T if T commutes with the projection PM. So now using the fact that every vertical operator is unitarily equivalent to a multiplication operator M sigma, and also the integral representation of the vertical operator in the form V phi, we have that whenever phi is coming from omega and V phi is bounded on A2 pi, then spectrum of V phi is same as its approximate spectrum is same as its essential spectrum, which is same as the essential range of the function M, where M is the M is coming from L infinity of R plus, and a scalar lambda is said to be a eigenvalue of V phi if and only if the Lebesgue measure of the set of all x so that M of x takes the value lambda is positive. Again, using the properties of multiplication operators on L infinity of L2 of R plus, we get that each V phi is normal and V phi is compact if and only if phi is zero. Also, the collection of all V5 is a maximal commutative C-star subalgebra of B of A to pi, and as we have seen earlier, that it equals to all vertical operators on A to pi. Similarly, if M is a closed subspace of A to pi, then it is a reducing subspace for all the operators in V, if and only if M takes the form V phi naught of A to pi, where this phi naught is associated to a characteristic function chi e for some measurable subset E of R plus. So this again follows from the fact that whenever we have M to be a closed, M to be a reducing subspace for multiplication operators, then we have the existence of chi e for some measurable subset of R plus, such that the set M is nothing but projection of it is nothing but the projection associated to the symbol multiplication operator associated to chi suffix e, which is an orthogonal projection. Now, if x comma nu is a measure space, in fact a sigma finite measure space, and H is a closed subspace of L2X, and if P of H is the orthogonal projection on L2 of X with range H, then for phi coming from L infinity of X, the Toeplitz operator T phi is an operator from H to H given by T phi of F is equals to pH M phi of F. So it is the compression of M phi to the space H. So it is known that if A is coming from L infinity of pi, then it is a vertical function if it is translation invariant, real translation. And it was considered in this paper of 2013 that if we consider C-star algebra generated by all the Toeplitz operator T suffix A, where A is a vertical function, then that C-star algebra was identified with the collection of all very slowly oscillating functions on R plus, where we say a function f from R plus to C to be very slowly oscillating if the composition of f, like f composition exponential function, is a uniformly continuous function with respect to usual metric on R plus. So using their result and using the integral form of the vertical operators, what we could see is we can explicitly give the integral representation for operators in the C-star algebra generated by Toeplitz operators TA with vertical symbol A. And they are precisely all those V5 belonging to B of A to pi, such that there exists sigma. Now it is coming from VSOR plus, such that phi and sigma satisfies again the same relation. So these are the references. So in the first two references, we consider a similar class of integral operators on the Fock space of dimension n, and we showed that in fact those integral operators are overlapping with the class of L invariant operators and separately radial operators on the Fock space. Now in the third paper, we actually give the integral representation of vertical operators. And now motivated by the first three papers, we also studied a similar class of integral representation for angular operators on the Bergman space. So this is the book for some operator theoretic results which I have used. Again, in this paper by Cao et al. In 2020, here they have considered the class of integral operators similar to what we have considered in vertical case, and they characterize the symbol for which the operators are bounded. So this is actually the first motivation to consider to see the integral representation for the class of commutative C-star algebra. Now again, these two are the books for some operator theoretic results. And in the last two things, vertical operators are discussed. In the last one, such operators are discussed on the upper half plane, and in the last but one, it is the results are extended to the vertical operators on weighted Bergman space over the upper. And these are the things I have referred for studying the various classes of commutative C-star algebras available on the Bergman space over the upper half plane, as well as on the Bergman space over the unit disk. Thank you.
Okay. Thank you very much for a nice talk. And please, question, comments? Something would like to ask?
Well, I just want to notice that Shubham Bais, jointly with his colleagues, found a very explicit representation of vertical, radial, and other types of operators. I think this is a good progress in this area.
Mm-hmm.
And I hope he will extend these results to more general situation with locally compact groups, etc.
Okay, yes, thank you, Igor. Other questions or comments? Well, let me return to my question. Basically, you define each vertical operator via function phi, which is analytic in the upper half plane, and satisfy some properties. At the same time, you have one-to-one correspondence between function sigma, which define multiplication operator, and connect to the function phi in a certain way. Function sigma form a sister algebra. So it should somehow translate algebraic operator to analytic functions on the upper half plane. Maybe it's worth think about this question.
Means here, if we consider the integrate form of phi, so this is something which takes the functions L infinity of r plus 2, some analytic functions.
So in fact, you in this form detected somehow sister algebra among analytic function on the upper half plane, but the operation are still unclear. Operation on sigma, it's trivial, but how to translate this operation to function phi, this equation.
Well, I think it is a very good question, but it probably has a simple answer. Please, Shubham, could you please show the formula for the integral operator V, V sub phi? Yeah, this one. Yeah, formula 2. So if we compose two operators of this form and apply some sort of Fubini theorem, we see that the new integral kernel is some sort of convolution of the original two kernels, but the convolution is performed with respect to the horizontal variable, and the imaginary, the vertical variable is fixed in some sort. Well, It will be some sort of convolution with respect to the horizontal variable and integration with respect to the second variable.
Anyway, it's good to clarify this question.
Yeah, it is very natural, very natural question.
Yeah, because to realize that analytic functions on the upper half plane may contain sister algebra with respect to strange operator, it's something interesting.
Yeah, some sort of convolution and integration.
Other question, comments?
Like one class of collection of symbols, analytic functions, which is closer to a C-star algebra with respect to some operation.
Okay. Well, sorry.
One thing I wanted to point out is the another motivation for considering the vertical operator representation of vertical operator was like initially the vertical operators were defined on A2 of pi, and we have the characterization for it. But now, since we have the integral representation, and we also know that if I take p in greater than or equal to 1 and less than infinity, then AP intersection A2 of pi is dense in AP. So we can also think of, means there is another related question. Can we say something about the boundedness of these operators on AP of pi? So we are not, the results are not clear for us right now, but this is some question which we could get it with using the integral representation form.
Okay. So thank you very much, Shubham. Very nice talk again. And hope to see you sometime in our seminar giving another talk.
Sure.
So Maribel, who's next?
Matthew is next.
Matthew. Okay, great.
Yeah.
So we will see all of you next Wednesday. By now, goodbye. Have a nice day.
Thank you, you too.